friction, more specifically surface friction forces. This is what we need to keep in mind. I'm going to plot F, particular force. I'm going to plot the magnitude of my frictional force F, which I will write little f. I will draw a linear behavior, straight line, a little dip, and then something that pretty much stays constant. Let's take the case of an object sitting on the surface where there is friction, and let's imagine that I'm pulling or pushing my object S with a particular force F, which is this one, towards the right. Let's imagine that the magnitude of this force F is 0, which means I don't push it at all. It means that on my axis I'm right here. According to this graph, the magnitude of my frictional force must be 0. Okay, now let me increase the magnitude of that force to, let's say, 1 Newton. That means I'm going to go towards the right, say 1 Newton. If I follow this graph, it tells me that the value of my frictional force must be, let's say my slope is 1, just to make life easier. 1 Newton. And we know that if I'm pushing towards the right, the tendency of motion of my object is towards the right. Therefore, since my frictional force is opposite to my direction of motion, it must be towards the left. So I know that my frictional force is like this. And I know that its magnitude is exactly the same as what I just applied. Okay? Let me increase my force even more. So of course I'm considering the case where I'm still at equilibrium. That is, even though I'm applying a force F, the friction is so high between my block and the floor that my system is not being accelerated. So let me keep increasing my magnitude. I keep increasing the magnitude of my force F, let's say to 2 Newton. And suddenly the frictional force decides to increase its own magnitude so that it matches exactly the one I just applied. And in this case, since again my system is at equilibrium, the sum of all my forces must be equal to 0. Therefore, the magnitude of F must be equal to exactly the same as the one I just applied to. So that's what the frictional force is going to do. It's going to keep increasing its value so that it matches exactly what is being applied to the system. And it will keep doing this until this point, which is what we call its maximum value. Since we've been considering the case where we're at equilibrium, which is also called static, we're going to call this little force static frictional force, or FS. So this little static frictional force will be able to increase its magnitude to match whatever is being applied to counteract it, such that the system remains at equilibrium. And it's going to keep doing this until its maximum value. So this will become Fs max. If the force that I'll apply to my object, big F, is bigger than this maximum value, then my system will start being accelerated. Let's figure out the magnitude of that maximum static frictional force. It is defined as follow: mu s n. This is the maximum force, or the maximum value, that my static frictional force can take. And this magnitude depends on two components: n, which is the normal force that we've seen earlier. So in this case, this one. So it's kind of weird. F is always directed along the surface, which many times will be perpendicular to the normal force, actually all the time. So it depends on a force which is not even in the same direction as itself. So that's n, and this, so that's a force in Newton, force, force. So mu s cannot be a force, otherwise it would be force to the square is equal to force to the power of 1. So since the units of n is Newton and the units of s is Newton, mu s must be unitless. There is no way out. So mu s is just a number, and mu s is always between 0 and 1. This is called the coefficient of static friction, which is a number between 0 and 1. And this number, the value of this number, will depend on the surface. The smoother the surface is, the lower mu s will be. The more rough and rugged the surface is, the higher the value of mu s. So, our little static friction can increase its magnitude all the way up to this maximum value. And then if I apply a force F, which is beyond this point, then this will not be strong enough, and therefore my system will start to accelerate. So in this range my system is moving. So all the way up to here, until the maximum value of my static friction, we're in the static range, or equilibrium. If you apply a force big F, which happens to be bigger than the maximum value that the static force can take, then the whole system will start to be accelerated, and we will call this range kinetic. When the whole system is being accelerated, then the frictional force will take a new value, and as you can see, this new value will be constant, and the value of this new force, new frictional force, will be mu k this time. So Fk mu k n. This will refer to the kinetic frictional force. So every time you have a system which is moving, either at constant velocity or increasing or decreasing velocity, the frictional force is known as the kinetic force, the kinetic friction. If the system is in static equilibrium, then we're going to be dealing with the static frictional force. Now obviously, the static frictional force changes depending on the force applied to your system, while the kinetic force, or the kinetic frictional force, is always the same. So the nice thing about the kinetic friction is, once you know n and you know mu k, that's it. It's always going to be the same value. Whether it's accelerating, decelerating, constant velocity, always the same. While the static friction can take a whole bunch of values, and the only way to figure out which is the value of your static force is by doing a free body diagram and obtaining all those little guys, all those little forces. Unless you're being interested in the maximum force that that static friction can take, then you can use USN. So keep in mind, never jump into using this functional form to figure out the static frictional force. In general, there is an infinity of value that this static friction can take. This one only refers to the maximum that it can take. And obviously, the kinetic friction is less than the static maximum friction, because this point is higher than this point. What does it tell us physically? It tells us that it's much easier to keep an object moving as there is friction between this object and the floor, rather than trying to get it to move. Because to get it to move, you have to apply a force which is bigger than this one. While if you want to keep it moving, you just need to apply a force which is bigger than this value. So there is a little margin between the two. That's what this little dip represents. Also, we can realize that there is a mu k and a mu s. This refers to, as we've seen, the coefficient of static friction, as the mu k refers to the coefficient of, as you can guess easily, kinetic friction. Similarly, mu k is between 0 and 1. But we can find a nice relationship between mu s and mu k. obviously if this is mu Sn and this is mu Kn, n is the same, mu Sn is obviously larger than mu Kn, therefore mu S is always going to be bigger than mu K. So for the same surface, mu K is always going to be smaller than mu S. So that is, if you have a particular object and a particular surface, you are going to have mu S and a mu K associated with this surface, and you know that the mu S is always going to be bigger than mu K. Typical value that you will see is mu S might be equal to 3.5, mu K might be equal to 0.2. That is, if you know the normal force, and let's say N is 1 Newton, then the frictional kinetic friction is 0.2 Newton, while the maximum static friction is 0.3 Newton. I'm sorry, 0.35 Newton, which means that to get this object to start to move, you need to apply a force which is bigger than this one. Then when it's moving, you can reduce that force from 0.35 to say 0.25, and it's still good. So remember, this is what we call surface friction. There is another type of friction, which is when we're moving an object not on a surface, but through a medium. We usually call this force the drag force. An example of this is as you walk through air, versus if you run very, very fast through air. Obviously, the faster you run, the more air you're going to feel, the more force is going to be hitting your face. Same analogy is in the water, or it's even more drastic. As you go through water, you're going to feel a force due to all those little particles of water going against your direction of motion. So when you're dealing with a system going through a medium, usually restate or rename that frictional force into a drag force. And this drag force is obtained by experiment and is usually proportional to the velocity, which means that the faster you go, the faster the drag force or the frictional force will be against your direction of motion. So for a rocket, which is going in a particular velocity v in this direction, there is going to be a drag force opposite direction, whose functional form is going to be proportional to the velocity of that particular rocket. If this rocket is going very, very fast and the velocity is very, very big, then the drag force will be now proportional to v to the 2, etc, etc, etc. So the faster you go, the bigger this number will be. Now in this class we will be dealing with drag force either proportional to a velocity to the power of 1 or the power of 2. So you will see Ft is equal to say AV, A being a constant obtained by experiment, or drag force is AV2, where A again is just a number which is obtained by experiment. So this is the functional form of a drag force as an object is moving through a medium, whose property is the faster you go, the stronger the magnitude of that drag force. This is different from the surface friction, which is for cases where an object is moving on the surface and there is friction between the two. Now you can add the two of them together. Technically, you could have an object sliding on the surface, therefore you can have the surface friction, and going through a medium, bang, you got the drag force. So technically you could have both if you wanted to. Usually we'll have problems treating them separately.